Design of axially loaded columns. Introduction of column. If a compression member and the effective length is greater than 3 times the least lateral dimension, that is called column. Normal columns are subjected to axial compressive force, but sometimes it may be subject to moments on one or both the axes. And the strength of columns depends upon, first, the shape, size and cross-section of the column, and the length. And for types of loading, first, axially loaded columns. Columns subjected to loads acting along the longitudinal axis or centroid of column section. Eccentrically loaded column or uni-axial loading. Loads which do not act on the longitudinal axis of the column section. Eccentrically loaded columns biaxial loading if eccentricity is with respect to both the axis x and y axis. The column is said to be under biaxial loading. So this is the diagram for axially loaded column, which is at the centroid of the cross section of the column, and this is the eccentric loading or uni-axial loading, one axis, and there's a distance x or e. For eccentric loading or axial loading or biaxial loading, we have the eccentric at e at x and e at y. And for members loaded in compression, the primary failure mode is buckling. And for axially loaded members are often also subject to other loads like bending and torsional loads. And for the design methods, in respect to columns subject to compression, it is important to note that limit for out of straightness is L or the length over 300 for timber sections and L over 500 for glued sections. And for failure due to buckling is caused by the following. First, inherent eccentricity of loading to centroid of section. Number 2, imperfections in timber cross-section and non-uniformity of timber material. The effect of these variables is to introduce initial bending with consequent bending stresses which result in failure much earlier than would result from compressive stresses alone. And failure due to buckling is related to is the cross-section of the column. Second is the slenderness and is the permissible stress of the material. And for Euler's column buckling theory, column buckling is a curious and unique subject. It is perhaps the only area of structural mechanics in which failure is not related to the strength of the material. A column buckling analysis consists of determining the maximum load a column can support before it collapses. But for long columns, the collapse has nothing to do with material yield. It is instead governed by the column's stiffness, both material and geometric. And it begins simply by noting that the internal bending moment in a loaded and deformed column is negative Py, where P is the compressive load and Y is the column deflection. So insert negative Py in for M in the bending or beam bending equation, or EI wide double prime is equal to M. So this is the external and internal forces, wherein within the internal forces or force we have the moment with a distance P or value P times Y. If the column is hinged at both ends, the Euler critical load is given as P critical is equal to pi squared EI all over L squared, and the Euler critical stress F sub E is equal to pi squared E all over L over R squared. So these are the formulas for Euler's column buckling. And for the effective length, real column do not have pin connected ends. The restraints placed on a column's ends greatly affect its stability. To counter these effects, an effective length factor K is used to modify the unbraced length. The product KL is called the effective length of the column. This length approximates the length over which the column actually buckles, and this may be shorter or longer than the actual unbraced length. And for the Euler's critical stress, F sub E, it is equal to pi squared E all over KL over R squared. Here's the diagram for the effective length factors, or K, for buckled shape of column shown in the dashed line, and the theoretical K value, and the recommended design value K, which will be used to multiply by the distance L and the end condition K. So in the first diagram, fixed support for both ends, fixed support at the lower end and the upper end, and this is the buckled shape of the column, and the recommended value for K is 0.65, which is 35% shorter than the actual length of the column. And for the second diagram, we have a fixed support and a hinge, and this is the shape of the buckled column, which is the recommended design value K is 0.80. And for the fixed support, and the other end is free to move, and the value, or K, is equal to 1.2, which is 20% greater than the actual length, or the unbraced length. And for our fourth diagram, we have a hinge. Both ends are hinge, or a hinge, and the other end is also hinge, and this is the shape of the buckled column, and the value, or the recommended value, is for K is equal to 1, which is the same value for unbraced length. So the effective length is also equal to the unbraced length. And for number 5 diagram, fixed support and no support at all, and this is the shape of the buckled column, and the recommended design value K 2.1. And for the last diagram, we have a hinge and free support. The recommended design value K is 2. So these are the effective length factors. And for slenderness ratio, it is defined as the ratio of the effective length to the corresponding radius of the gyration of the section. Slenderness ratio is equal to LE over R, or KL over R, where L is the actual length of the column member, LE or KL is the effective length, R is the appropriate radius of gyration. And for short column, the value for slenderness ratio should be less than 50. And for the intermediate column, it should be the slenderness ratio is between 50 to 250. And for long column, the slenderness ratio is greater than 250 or above. And for the critical slenderness ratio, or C sub CR, the critical slenderness ratio C sub CR corresponds to the upper limit of elastic buckling failure, which is defined by an average column stress equal to 0.5 Fy. And the formula for critical slenderness ratio, or C sub CR, is equal to the square root of 2 pi squared E all over F sub Y. And radius of gyration. Radius of gyration, or gyradius of a body about an axis of rotation, is defined as the radial distance to a point which would have a moment of inertia the same as the body's actual distribution of mass if the total mass of the body were concentrated. And the formula, or K sub y, the small k, is equal to the square root of I sub y all over A, or the cross section of the column. And I sub y is the moment of inertia along y-axis. And for allowable unit stresses in PA, or Newton per millimeter squared, of cross-sectional area of square or rectangular simple solid columns shall be determined by the following formulas: but such unit stresses shall not exceed values for compression parallel to grain, or F sub C, in accordance with the provision of sections 3.4 of the National Structural Code of the Philippines. So number 1, for short columns, the ratio of LE over D is 11 or less. And we will use find the allowable compression stress, or FC prime, is equal to, which is also equal to the compression parallel to grain, or F sub C. And that's for short column. And if the column is an intermediate column, the ratio LE over D is greater than 11 but less than K, where K is equal to 0.671, the square root of E over F sub C, and we will use the allowable compressive stress formula, or FC prime, which is equal to F sub C, open parenthesis, or multiplied by 1 minus 1/3 of LE over D all over K, open close parenthesis, exponent 4, and close parenthesis. And this will be used if it is an intermediate column. And last, long column, LE over D is equal to K or greater. And we will use the allowable compressive stress, or FC prime, which is equal to 0.3 E all over LE over D square. Example: a timber column of square cross-section has a length of 3 meters and a dimension of 140 mm by 140 mm. It is hinged at the ends so that K is equal to 0. Compressive strength F sub C is given on the specifications, and also a table of timber with their corresponding working stresses for visually stress graded unseasoned apitong with 80% stress grade. And the modulus of elasticity, or E, is equal to 7,310 megapascal, and this is for apitong. Compression parallel to the grain, or F sub C, is equals to 9.56 megapascal. And for the question, is the column A a short column, B intermediate column, C long column? Number 2, which of the following gives the allowable compressive stress? And number 3, which of the following gives the allowable axial load? So we have a column, and the cross section of the column is 140 mm by 140 mm with a length of 3 meters and a concentrated load P, which at the center of the cross section. Solution: let's find the ratio of the length over the cross section B, L all over T, and it is equal to the length of the column, which is 3 meters, and D of the cross section is 140 millimeter. So we convert meter to millimeter, which is 1000 millimeter over 1 meter. The ratio of the length over the cross section D, which is equal to 3000 over 140, or 21.43. And to find K, formula for K is equal to 0.671 and square root of E over F sub C, where E, the modulus of elasticity for apitong with 80% stress grade, it is equal to 7,310 megapascal, while F sub C, or the compression parallel to the grain, that's 9.56 megapascal. And we substitute the values in the formula for K. 0.671 square root of 7,310 all over 9.56. So megapascal over megapascal. And the value for K, 0.671 times the square root of 7,310 all over 9.56. And the value for K is 18.55. The ratio L over D, which is equal to 21.43, is greater than the value K, which is equal to 18.55. Therefore, the column is said to be in a long column. Therefore, it is a long column. Next, we will find the allowable compressive stress. Number 2, allowable compressive stress. And the formula, because it is a long column, we will use the allowable compressive stress formula. F sub C prime is equal to 0.30 E all over L over D squared, and 0.30 times E, which is 7,310 megapascal, and we divide by L over D, which is equivalent to 21.43 and squared. And the value for allowable compressive stress, or FC prime, is equal to 4.78 megapascal. So this is the allowable compressive stress. And last, which of the following gives the allowable axial load? So number 3, allowable axial load. And the formula, Fc prime is equals to P over A. And to find P is equal to A multiplied by Fc prime. And the cross section of the column is 140 millimeter by 140 millimeter. 140 times 140 is the area of the cross section, and multiplied by Fc prime, 4.78 megapascal. And the value for P is equivalent to 33,688 Newton, or in terms of kilonewton, we divide by 1000, or it is 33.69 kilonewton. So P, or the allowable axial load, is equal to 33.69 kilonewton, and this is the answer. Number 2, a steel beam is used as a girder with 7.3 meter span, carrying a total uniform load of 145 kilonewton per meter, including its own weight. Properties of steel: modulus of elasticity, which is equal to 200,000 megapascal. Moment of inertia, I of x, is equal to 723 times 10 to the power 6 millimeter exponent 4. And for the properties of wood, allowable compressive stress parallel to the grain is equal to 10.35 megapascal. And modulus of elasticity for wood is 13,790 megapascal. And for the question, which of the following gives the deflection at the midspan? And number 2, which of the following gives the allowable axial load if the wooden column height is 3 meters and a cross section of 250 millimeter by 250 millimeter. For question number 1, which of the following gives the deflection at the midspan? The deflection. This is the beam with a weight of or a uniform load of 145 kilonewton per meter, including its own weight, and we will find the deflection. Number 1, the deflection at midspan. And the formula for a uniform load with a simply supported beam, and the formula for deflection is equal to 5WL exponent 4 all over 384 EI. And the length, so the length of the beam is equal to 7.3 meter. The uniform load, which is 145 kilonewton per meter. E, modulus of elasticity for steel, 200,000 megapascal. And for moment of inertia, it's 723 times 10 to the power 6 millimeter exponent 4. So substitute the given, so equal to 5 times W, which is 145 kilonewton per meter, or 145,000 newton per meter, and the length, which is 7.3 meter exponent 4, and we divide by 384 times 200,000 megapascal, 200,000 megapascal, and multiplied by I, which is 723 times 10 to the power 6, and to convert, we multiplied by 1000 cube, and this will be in millimeter. So the deflection, so 5 times 145,000 times 7.3 exponent 4, and multiplied by 1000 cube, and we divide by 384, and also 200,000, and 723 times 10 to the power 6. The value for the deflection is equal to 37.08 millimeter. So this is the deflection at midspan. Number 2. Which of the following gives the allowable axial load if the wooden column height is 3 meter and a cross section of 250 millimeter by 250 millimeter? So this is the column, and we have the axial load P with a cross section which is 250. This is 250, and this is also 250 millimeter. So let's check first the ratio L over D, and the length of the column is 3 meter or 3000 millimeter, and the dimension of the cross section, which is 250 millimeter or D, and the ratio cancel out, 3000 over 250, or equivalent to 12, and that's L over D. And to find the value for K, which is the formula 0.671 square root of E over F sub C. And we will be using the properties of wood E. So for wood, E is equal to, based on the given, it is 13,790 megapascal, and the F sub C, which is 10.35 megapascal. And substitute the given values, so 0.671 and square root of E 13,790 and divided by F sub C, or 10.35. So the value for K is equal to 24.49, which is greater than the value of L over D, that is 12. Therefore, the column is an intermediate column. Because it is an intermediate column, we will find now the allowable compressive stress based on the intermediate column, which is the formula allowable compressive stress and the formula for intermediate column FC prime is equal to F sub C, open parenthesis, 1 minus 1/3 times the ratio of L over D over K, or L over D over K, and open close parenthesis exponent 4 and close parenthesis. F sub C, that's 10.35, 1 minus 1/3, and L over D is equal to 12, while K is 24.49, and open close parenthesis exponent 4 and close parenthesis. So F sub C prime, so 10.35 times 1 minus 1/3 of 12 over 24.49, the value is, and exponent 4, the value is equal to, or F sub C prime is equal to 10.15 megapascal. Once you solve the allowable compressive stress, you can now determine the allowable axial load. So allowable axial load, or P, so F sub C prime is equal to P over A, and to find P, that's A F C prime, and the cross section of the column is 250 by 250, so 250 by 250, and FC prime is 10.15, so 10.15, and the value for P is 375, and it is in Newton. To convert it in kilonewton, we divide by 1000, so P is equal to 634.38 kilonewton, and this is the allowable axial load, and this is the answer.